In this video, I'm just providing you some regression help to help you with the regressions that we did in class. It is essential for you to know this definition. If you have not rehearsed it to a point of knowing, you need to start, because this is going to be worth a lot. The precise definition of mathematics is the technique to explain, understand, and manage reality by ciphering, counting, measuring, classifying, ordering, inferring, and modern patterns arising in the environment. This is essential because this is what math really is. I know you kids like to go to Google. If I ask you what is mathematics, you go Google something crazy. This is what you need to know. It's not about just shapes, trig, geometry, algebra. Those are parts of mathematics. That is not the precise definition of mathematics. Alright? Steps. I decided to give you 5 steps to get through regression. And this should help you. Alright, step 1, put in your models to determine the correlation level. R being linear, R squared being either quadratic or exponential. Step 2, describe the relationship. Remember, correlation is between 1 or negative 1. It's between those two numbers. That's what you're looking at. If it's perfect, 1 or negative 1, it's a perfect relationship. Strong only if is it 0.7 or negative 0.7 or closer than that. It's weak when it's negative, when it's 0.6 or negative 0.6 and further away from positive or negative 1. Alright, if it's 0, there's no relationship. So y'all, at times, you may have to look at the graph at times to kind of give a up-close analysis. From there, there's 2 steps. Step 3, create your equation based on the highest R or R squared value. Look at your coefficients. A, B, C, M. You know, those are the main coefficients. So A, B, C, or M. Keep those in mind. And then last, put everything in complete thought. And sometimes you could put all these in one step. You could do all that as just one little situation. But I'm going to go slow by slow throughout the video. Correlation. So y'all remember, correlation has a good piece to it. Before you could talk about the correlation, you got to talk about the data. The data is numbers taken from a situation or experiment. Like for example, our ANET data, the experiment was the test, and the scores that you did on ANET became the data. Alright? Or your grades and the work you turn in. That is also data. So it starts off with that. And then from there, the data is analyzed to determine the relationship between the dependent variable and one or more independent variables, which is x. So in hindsight, from the data, correlation is the relationship between the two variables of your data. Correlation sometimes will be called trends. We are dealing with polynomials and non-polynomial trends. And then from there we create regression models based on the patterns in the experiment that best represent the data closest to the correlation, so -1 or 1, to make predictions of the situation. this may be, this is step two. So I'm going to give you a table, test, anything like that, and you have to describe it. So let's talk about the correlation. Well, you don't know the R value either, but you do know that that forms a shape of a line, and most of the points are forming helping that shape to happen. So from there, you could say there's a strong relationship between the high temperatures and the number of tickets sold. However, this is how you need to write it. The scatter plot of the positive correlation shows a positive correlation, because as the daily high temperature increases, the number of admissions tickets sold increases. So this is how you're supposed to write it. As something increase, another increase, which is a variable. So you can't say X and Y increase. You no longer can say that when given a real life situation. So you cannot. So this is how you explain that. The other stuff, you could say that too, but that's fine. But that's why I want you to do in the yellow. The yellow is what I need for you to describe every correlation when I'm giving to you as a table. I mean, as a graph. Sometimes I may tell you to, hey, describe the whole thing in detail. This is what I'm referring to. Just like that. It is a positive correlation because as something increased, another situation increased. This that I highlight in red, I'm trying to highlight in red, I guess I highlight in blue if it could work. Or orange. This will give you some credit, but not full credit. So while I highlighted orange, it's cool, but it don't give you enough credit. Only because you just looked at that, it just gave me basic description. What's in the yellow is the description you need. Okay, I can move on. Not forget that correlation is from -1 to 1. The closest to -1, closest to +1. If it's 1 is perfect, I already told you. So I'm not going to go any further than that. That's something we talked about already. So again, this is going back to the water park example, how we were able to make an inference on the correlation relationship by looking at those points. When they form close to forming a solid shape, like a line in this case, it's a perfect correlation. When it's come close to is a strong relationship, but when it's all over the place, it's weak because it's not really forming anything. So do not forget, correlations could also be quadratic as well. And I'll show you a better example than that. Again, the R values. But yeah, I want you to pay attention to the -1. -1 does not mean that there's a weak relationship or nothing like that. It's a strong negative relationship. For example, your grades being dependent variable and your work being your independent variable. grades decrease when you turn in less work, or your grades decrease when you have behavior issues, which is true, all right? So keep that in mind. You're looking for the R values that are the highest number. So let me clarify something here right quick. You're looking for the highest R value. I know when I say closest to 1, you guys tend to get confused on that. So let me reiterate. The highest R value. So here's an example. In my water park situation, I only did 1 out of the 5 steps. Because I had just only a graph to look at, that's just made a difference there. Here, you got a table now. You gotta find the model that best determine the relationship between x and y. So again, I go to decimals, plug in my models here, here, and here. I'm looking for the highest R value. I realize that the highest R value or R squared value is 1, and that's when it is quadratic. And because it is 1, I could say there's a strong relationship or a perfect relationship between x and y. It's perfect. From there, I gotta create the equation. To create my equation, I gotta look at the parameters. And since I'm using this model, my equation gotta look like this. I gotta get rid of the subscripts. Subscripts not allowed because you don't have equations that have subscripts in math unless you are doing science. So ax squared plus bx plus c. Alright? So looking at my parameters, a being negative 7. So because it's a quadratic, my equation is negative 7x squared, and the correlation level is again strong between x and y. These are examples of data, the little dots you saw on the graph, form into various shapes. Again, all these are perfect correlations, except for here, because that's strong but not perfect, because all the dots are forming shapes. Well, most of these are strong, some of these are perfect. But again, when the dots are forming this shape, the data points are forming this shape, you got a strong, if not a perfect correlation. Moving on. Correlation drama. Some of you students caught on to this. I didn't pay attention to this, so I want to thank you guys for pointing something out to me. So sometimes you have linear and a quadratic both have one as correlation. So when that happens, you gotta look at the particular cases. So the examples of the equation of x plus b and y is the quadratic. So what you're looking for, pay attention to the quadratic first. You see how a is 0? When a is 0, it's not quadratic. Quadratic means that you have an exponent of 2. Your leading exponent is 2. So when I have 0x squared, guess what happens to my quadratic? All that's going to be turned to 0, which is going to be 1. And I'm left with this guy right here. Linear has an exponent of 1. This goes back to the law of exponents, remember? Remember, quadratic has an exponent of 2. So in order to keep that exponent of 2, a has to be above 0. A must be above 0. Because if it equals, it's not quadratic. Alright, we good on this? Again, When you have a situation when linear and quadratic are both 1, look at the quadratic. If the quadratic has the coefficient of a being 0, that is not quadratic because it turns your exponent to, it makes it disappear. I know I said 1, but that's not the case. 0 to any power is 0. So that's what happens. Again, one more time. If R is 1 for both linear and quadratic, look at quadratic. If the A is 0, it is not quadratic because 0 to any power is 0. And the quadratic is the exponent 2. You need the exponent to be 2. 0 to the second power is 0, so it's not quadratic. Alright, I think I said enough about that. And you guys are good with correlation and causation, so I'm not worried about that. This is just an example of what it means to be correlation. Correlation just means there's a relationship. Does it make sense? No. These are 3 examples of correlation, but they're not causation because causation means there's a relationship that has a cause and effect. Like your grades and your work, that's a cause and effect. When you don't do the work, you don't get the grade. Here's a question for you. I give you 10 seconds to read, or 30. I'm going to click the answer and move on. Starting now. The answer is A, because burning candles is associated with a better smell room. If you like candles, they're going to have a pleasant smell. Most of them. There's only a few occasions where there's candles that smell bad. Well, they smell good to some people, but smell bad to others. Again, don't worry about that. Well, regression, as I have told you before, taking notes from a situation, refer to the experiments called the data, and when we get the regression, we just model it. So here's the data. Now I'm going to model the regression. Well, I have a regression model. So the graph, we already did this before. And again, my M, I want you guys to understand, when I created the model, I know it's a perfect relationship between X and Y. I'm not worried about that. But again, I took the model, M being 1, because the equation, which I rewrite that, Y equals mx plus b. Again, you must have an equation. This is a model, but not an equation. So m is 1, so I got x. 45. So I took those 2 of my parameters, and I created my equation. That's how you do it. Look at the parameters, create your equation from there. Here, I'm doing the same thing because again, I took from my parameters. I know that the correlation is 1 is perfect. Look at my parameters. I created my equation from my parameters. But because b and c is 0, I'm not worried about b. I'm worried about y equals ax squared. If I was worried about b and c, that means b and c would be greater than 0. Then I would have y equals ax squared plus bx plus c. And again, I'm just taking this model, I'm turning it to an equation. Do not forget, you do not have subscripts for equations. You must get rid of your subscripts when you are making your equation. You must get rid of your subscript when you are creating your equations. You must erase your subscripts to create the equation. I'm done. And it's the same thing here again. I created a graph. Another graph helps me describe my relationship. And the R squared 1 is perfect. And C, the parameters, A and B equation. Alright, I know I didn't write the equation there, that's alright, but here's the steps again. But this time, I have to use these steps and apply them to situations. These are the steps. Applying your regression models to determine your correlation, describe your relationship, create your equation based on your highest level. Now, 4. In this part, that's what I'm most worried about. I'm trying to find the dependent variable given my independent variable and vice versa. Remember, dependent variable is y, independent is x. And then you must put everything in complete thought. Now, let's analyze some data. Again, the steps are there again. Put your models in, describe your relationship, follow the rules of determine which kind of relationship it has based on the levels, create your equations, dependent models or independent, depending on what's being asked of you, and put in complete thought. So here, I'm here to analyze the slope. On rare occasions, you may have to ask a question like this. You know it's linear, so you're not worried about the 5 steps in this. And you're just trying to describe the equation. So when it's linear, you describe the equation by looking at the slope. And the slope is going to be your m. And so where's m located at? M is always in the front. Remember, linear always represents m. So if you are struggling with that, go back to the models that we did, pause, and take notes on that. So I know I have a negative slope. I have an independent variable of lunch breaks, and I know I have a dependent variable of cells or bicycles. So I could make, going to step 1, the correlation. I don't have the values or nothing like that. I can say from this that because the slope is negative, the longer the lunch break, the less bikes he or she sells. And that is all you have to do when I'm telling you to analyze the slope or analyze a linear equation. Alright? So rewatch anything that you got lost on. I'm moving on. Right. So with that being said, let's go use the 5 steps that we have learned and apply them. So Emmett is writing an article for an online music magazine on why some bands last longer than others. While researching the article, he compiled information about how long various bands have lasted without changing their lineup. On comparison, he looked at was between the number of members in each band X and the number of years each band has lasted Y. Alright, so I know I don't have any directions of telling you what to do, but we're going to go ahead and apply those 5 steps in order. So I am putting this in decimals right now. You won't see it, but I'm putting it in. And so when I put this in decimals, I realize that this function is linear because it has the highest R value, which means as the band increase, the duration of them lasting decrease. And so when something increase and decrease, it is a strong negative relationship. All right, strong negative. All right, so I did that. I put in my models. I describe who had the highest R value, and then from there, I describe the correlation of the highest R value. And now I gotta create the model based on the highest R value, which is that. Okay. 4, I have been asked a question: how many years would be in that band that lasts? No, how many members would be in the band that lasts 7 years? So I'm giving some information. I gotta find something, but I'm giving something. So which one is the independent variable? The members in the band. What's the dependent variable? Years. So here, you got members and you got years. So the years is the X or the Y. The years is the Y value. Because it's the Y value, I gotta take 7 and plug it in for the Y value. And from there, I put this in decimals. And when I put this in decimals, I get an approximation of close to 10. So now I'm ready to put my complete thought in. Again, before I move on, I took 7 because 7 was the years, and 7 is the dependent variable, which is y. And I got rid of the y, and I put in 7 for y. And then once I plug it in to decimals on the graph, the x-intercept is going to be like 9 point something. So, which approximate to 10. Now with that being said, I can put everything in complete thought. Our model y equals negative 2.849x plus 34.604 predicts that there will be approximately 10 members in the band that will last 7 years. I did all 5 steps just like that. So you will have to do the same exact thing. This is what you have to do. I described the correlation based on my models who had the highest correlation. I described that. And then from there, I created my model. But do not forget, you're looking for the highest R value that is the closest to negative 1 of 1. So put those in and look and see which one is the closest to either negative 1 or positive 1. Closest to, closest to, closest to, closest to the R value. You saw the example. This example we did in class several times. And I'll tell you this quadratic. So you gotta use step 5. Take what you know and answer the question. So I'm trying to find out the minimum temperature when the maximum temperature is 90. So because it's quadratic, this is the model. And again, because I'm trying to find the minimum, but I know the max is 90, just plug in. And then I put it in complete thought. Again, you must make the prediction. The prediction is the last step. It is key. This is key. So, in this problem, I was more focused on creating a model, which I told you was quadratic, and to make a prediction. Remember, I was making a prediction given the facts. Moving on. Same thing here. I told you this was exponential, and we had to answer a question, which is to make the prediction. Now, you don't have to worry about step one, step two, because we already know all that. We're going for step 3, 4, and 5. Step 3, known as exponential, create your equation. 4, finding the information. And 5, answering the question. So in 4, I did it in one step. 4 and 5 became 1. Again, you plugged into values. So the 18th hour was plugged in here to be X. So I got rid of X, I plugged it in. So this is very similar to everything else we just did. So review this information. Last and least, answer this question. You may want to know this answer because it's going to be on your test, quiz, Kahoots. How does regression satisfy the precise definition of mathematics? I'll leave it there.